All right, let's talk about something that can be a real headache for any Python developer: memory management. It's that invisible force working behind the scenes that can either make your code super fast or bring your entire machine to a grinding halt. Today, we're going to pull back the curtain and figure it all out.
We've all had this moment, right? It's late, you're trying to get a project done, and suddenly everything just stops. Your computer's fan starts screaming like it's about to take off, and you realize Python has somehow devoured all your RAM. It is so frustrating, and it makes you wonder what on earth is going on in there.
And that really begs the question, doesn't it? We're always told that Python is great because its memory management is automatic. We don't have to fiddle with memory like you would in C or C++. So if it's all supposed to just work, why do our programs still crash and burn from memory errors? Okay, let's get into it. Python's memory model isn't some kind of black magic. It's actually a pretty clever system that relies on two main ideas working together, something called reference counting and a garbage collector. Once you understand how these two play together, everything starts to make a lot more sense. So the main workhorse here is reference counting. The idea is actually pretty straightforward. For every single object in your code, whether it's a number, a string, a list, whatever, Python keeps a little counter. This counter tracks how many different variables are pointing to that exact object. The second that counter drops to 0, Python knows nobody needs that object anymore, and poof, the memory gets freed up for something else. Let's see this in action. It's pretty cool. So we create an empty list and call it x. Now, you'd think the reference count would be 1, but it's actually 2. Why? Well, one reference is our variable x, and the other is a temporary reference from the function we're using to check the count. Now, watch this. When we say y equals x, both variables point to the same list, so the count bumps up to 3. And then when we delete y, the count just drops right back down. It's just simple bookkeeping, happening constantly. But, and this is a big but, reference counting has a blind spot. It's something called a circular reference. Imagine you have two objects that are pointing at each other. Even if nothing else in your program needs them anymore, they're still keeping each other's reference count above 0. They're basically keeping each other alive, creating a memory leak that reference counting can't see. And that is exactly why Python has a garbage collector. You can think of it like a safety net or a specialized cleanup crew. It runs every now and then in the background, and its one job is to hunt down those little isolated islands of objects that are only referencing each other. When it finds a cycle, it's smart enough to break it and free up that chunk of memory that would have been lost forever. So now that we know how the system is supposed to work, let's talk about how we, the developers, can mess it all up. We're going to look at 3 super common memory traps. These are the little mistakes that are so easy to make and can cause your program's memory to just balloon out of control. Okay, trap number 1 is by far the most common offender: reading a massive file directly into a list. You open a file, loop through it, and append every single line to a growing list. Before you know it, you're trying to hold a multi-gigabyte file entirely in RAM. The fix for this is so elegant. Use a generator. Instead of building a giant list, a generator gives you one line at a time, lets you process it, and then forgets about it. Your memory usage stays totally flat. It's a game changer. Oh, this trap is practically a Python rite of passage. Using a mutable object like an empty list as a default argument in a function is a huge no-no. Here's why. That list gets created only one time when Python first defines the function. That means every single time you call that function, you're sharing and modifying the exact same list. The proper safe way to do it is to default to none and then create a brand new list inside the function, every time. Now, our third trap is a bit sneakier. It has to do with hidden references, often inside things called closures. This happens when you have a function inside another function. The inner function can remember and hold on to variables from the outer function. So if that outer function was dealing with a huge chunk of data, the little inner function can keep a reference to it, preventing that memory from ever being freed long after you thought you were done with it. Okay, enough with the problems. We've seen how things can go wrong. Now let's talk about how to fight back. We're going to build up our arsenal with some specific tools and techniques you can use to hunt down and fix these memory issues. First up is a fantastic Python feature called _slots_. See, by default, every object you create from a class uses a dictionary in the background to store its attributes. Dictionaries are super flexible, but they use up a decent amount of memory. But if you have a class where you know exactly what attributes it will have, you can define _slots. This tells Python, hey, don't use a dictionary, use this much more compact, fixed size structure instead. You trade a little flexibility for a big memory win. And the difference can be absolutely massive. I'm not talking about a small optimization here. If your code is creating thousands or even hundreds of thousands of these objects, switching to underscore slots can literally save you hundreds of megabytes of RAM. But here is the single most important piece of advice. You can't fix what you can't measure. Don't just guess where your memory problems are. Optimizing without data is just stumbling around in the dark. You absolutely have to profile your code to see where the memory is actually going. And the best tool for this job is already built into Python. It's called tracemalloc. It is incredibly powerful. All you do is start it, run the part of your code that's causing trouble, and then take a snapshot. It will literally point you to the exact file and the exact line number that is allocating the most memory. All the guesswork is just gone. So let's pull all of this together into a clear, repeatable strategy. The next time you think you have a memory leak, this is your step-by-step plan of attack. And here it is, your memory cheat sheet. Think of this as your go-to guide. If you see memory usage constantly climbing, your first suspect should be an accumulating list, and the fix is probably a generator. If memory stays high when you think it should have dropped, you might be looking at a closure capture or a pesky circular reference. This table connects the symptom directly to the cause and the solution. So we've looked at the whole system, from reference counting to the common traps we all fall into, and the tools like tracemalloc that help us find them. In the end, mastering Python's memory isn't about memorizing a bunch of rules. It's about understanding the system so you can work with it, not fight against it. So that just leaves me with one final question for you. What's the absolute weirdest, most confusing memory bug you've ever had to track down? Thanks for tuning in.